fuel and lubricant research and development. So please excuse my mask because I'm in an office now and I'm required to wear mask all the time. If not, somebody gonna report me to HSC. So today, we are gonna present a paper on modeling of base oil processing using extreme gradient boosting and SGB approach. So this is a bit of disclaimer. So this will be my presentation outline today. So I will start with who we are, the background problem statement, the method and result of how we approach this problem, and the conclusion and way forward. So who we are Petronas. We are a Fortune 500 company. We are fully integrated oil and gas business from upstream to downstream. And we are strongly guided by our statement of purpose, where we are a progressive energy and solutions partner, enriching life for a sustainable future. So we are also a global lubricant players. I guess we don't need to talk much about that.
So, can you hear me well? Yeah. So, good afternoon. Welcome to our first technical sessions this for ICIS 2021. In today's sessions, my name is Tang. I'm from the E departments of UTP. I'm chairing these tracks on artificial intelligence. We will have a total of 7 papers this afternoon, starting from 12:05. So we have about 3 minutes to go to start our first speakers. So we have 7 very exciting talks, including coming from the industries, from Petronas itself. Also, we have international speakers coming from KAU, Saudi Arabs, and also papers coming from UTPs. I think that let's wait for about another 3 minutes for us to wait for the participants to come in, the viewers to come in, and we will start the session sharp at 12:05. Right. So I hope everyone's staying safe and healthy despite the challenges of these pandemics. Now, in today's sessions, the presenters will share. We will share the presentations coming from all the papers, and they are in the pre-recorded form. So, but however, we have the presenters with us online. So if you look below, there's options there on live Q&A. You can enter the questions that you have, and I will help you on your behalf to actually raise the questions to the presenters, and our presenters will then replies to your questions. We hope that we have very engaging sessions this afternoon. So please do send in all the questions that you have for the presenters. Or if you have any other questions, please raise it. I think that we hope that we have a very engaging sessions over here, right? So I think that we wait for another 1 minute or so to start at 12:05 according to the schedules. So this is the sessions, and then just to share with the audience that do participate this afternoon. We have the official launch of ESCON. They are very exciting and very. We have the plenary speakers, prestigious companies, and so do join us for this later, especially in the afternoon session as well. Okay. Now, in the first talk, we will have Encik Ashraf Zain from Petronas. He will share with us on his papers on modeling of base oil processing using extreme gradients boosting approach. Right. So we will start his talk at 12:05. I think maybe Haja can launch his talk.
We are the title sponsor, technical partner for the AMG Petronas Formula One team, where we are the world champion for 7 times in both constructor and driver championship. So, as a fluid technology solutions department, we supply fuel, Petronas Premix, we supply lubricant, we also supply the transmission fluid to our F1 cars. So, if you are not familiar with what we call base oil, so base oil is the major component of lubricant, usually about 90 to 95% of the lubricant composition, and the rest made of additive. So we also have a base oil processing plant. We call it Malacca Group 3, and it was one of the first plant in the world to produce Group 3 base oil from atmospheric residue from the distillation column, or we call it as SWR. And why the reason why we want to do this project using all this digitalization effort is we want to reduce the product quality giveaway and improve the yield. And we also strongly believe that all this digital transformation effort could help us to improve the productivity and the plant efficiency. So, as I told you, we have a Malacca Group 3 base oil plant producing base oil from atmospheric residue. So we are motivated to develop an integrated models that could quickly predict what are the specifications, what are the quality of the intermediate and final quality of the base oil, and simultaneously use this model to optimize the values that we got out from this base oil plant. So if you can see here, usually conventionally when we want to use when we want to predict this process, we need the kinetics data, we need the thermodynamics data. We usually use first principle. So the idea of this project is trying to use all the data that are available to us from all those operating parameters of the plant, of the reactors, and all the specification of the feedstock that we use to predict the final outcome, the specification or the quality of the base oil that we produce, which is the lube base oil or LBO. So when we look into all these wet sea feedstock properties and also at the process parameters, we have about 30 to 40 input, or we call them as input factor or axis. And we also have a lot of output or response that we like to analyze. But today we're just going to focus only on one loop based on viscosity index VI, which is the most critical thing. So what is machine learning? I think it's already 2021, so I guess I didn't need to really like advocate this machine learning anymore. It's already like very widely spreadly used outside, even in oil and gas industry. So there's one quote by professor in University of Washington, Professor Pedro Domingo, saying that machine learning algorithm can figure out how to perform important tasks by generalizing from examples. So all it does is just trying to figure out what are the patterns. So as I mentioned before, the old conventional way of modeling a process like this, which is hydroprocessing, is trying to use first principles, which rely on kinetics and thermodynamics data. But sometimes even that one could get very complicated because considering that we are processing something that is very heavy hydrocarbon, and sometimes assuming first principle, first order reaction is not going to give us the accuracy that we want. And then nowadays, machine learning is becoming more popular with increasing computing power and wealth of data. Like I said, we have a lot of data gigabytes, even terabytes of data from our processing and refinery plant. And nowadays, various machine learning algorithms are publicly available, so you don't need to, or we don't need to develop our own machine learning algorithm. And then the popular ones that we have tested include gradient tree boosting, or better called SGB, and also ANN, artificial neural network. So going a little bit into the method, so this is the workflow that we use when we develop our machine learning model for this process. So the very first step, which include data collection and pre-processing. So we collect the data from our pilot plant and our real commercial plant, MG3. Excuse me. And then we did a lot of pre-processing data to make sure that we do not feed garbage data into our model. So some of this pre-processing include removing the outlier. We use a technique called principal component analysis, and then we normalize and transform all this data. And very important step is we split this data into training and validation data set using ratio of 80-20. So this training and validation data set splitting is very important to make sure that we are not overfitting or we are not overtraining uh, our model. And then the next one is we develop this machine learning model on the training data set, and we look at the accuracy, which is we use root mean square error and also mean absolute error, and we compare it with the ASTM of the R method of the each ASTM. And then we also look into how we could improve the model by hyper-tuning the hyperparameter, and at the same time we as the so-called domain knowledge expert of the process engineering, we look at counter check what the model is telling us with the kinetic and thermodynamic facts. And then we also use the model validation to make sure what we develop is not very far off. So this is just a snapshot of our data pre-processing. So as I mentioned, we split it this data into training and validation data set at 80-20 ratio, and we use principal component to make sure that when we split all this data into two training and test validation data set, we use random splitting, and we use principal component and t-test to make sure that we are not really splitting this data with biases. And all these f-tests shown that we don't have those kind of biases. So we could use this two data sets to proceed with the model development. And another thing that all these principal components tell us also that when we look at all these 38 variables or these 38 axes, the first four principal components could only explain 80% variance in the 38 axes. What does this mean is that this process is not a simple it's not a simple problem that we could model the whole process by just using principal component analysis. And I also want to show you that here, when we did all this, when we graph out all these principal component, we could see mainly three groups of data set. And this is kind of jive or agree with what we understood about all this process. So basically, there are like three grades of all these base all. So moving on, like I said, we look at many response or many Y outcome, but we are just going to focus on viscosity index of this lubricant base oil. And we split them into two grades, which is atro 4 and atro 6. It's very important because even the reproducibility of this ASTM 2270 shows there are two different numbers of reproducibility for different grades. So for example, for atro 4 is about 5.0 and VI of atro 6 is about 3.8. And if you want to be more strict about this accuracy, we can divide it by about 3, which is 1.8 and 1.4. So what we found out that from the root mean square error, the accuracy of the training data set for this model, we got about 0.78 for atro 4 and 0.2 for atro 6. And when we test the accuracy of the validation dataset or the test dataset, where we didn't even use this dataset to develop the model, we also get the same or very close accuracy to the training dataset, which is about 0.65, 0.2. And what does this tell us is that this model is good. And at the same time, because there is a little differences between these two numbers, we could say that we didn't really overtrain or overfit this what we call this model, this processing model. So if there is a big difference between the RMSE of your training and test data set, that could indicate that we have a high bias or we have an overfitting issue. And remember that we did the data splitting and we look at the T test that we determine that we split them evenly, that there is no bias. And then another accuracy that we look at is a mean absolute error of the test dataset. We like to use this because sometimes the RMSC just amplify any outlier that you might have. So we also look at the t-test, f-test, and the r-squared. R-squared is like very old way of looking at the accuracy, but our refinery people wants to look at this, we just provide to them. So all of them are pretty good. So the second one, SGB model.
Right. Is that Encik Ashraf? Is it?
Yep.
Yeah, I think that probably because of the time, I think that maybe they have restricts the time for the presentations. So thanks for very, very interesting talks that I was hoping to hear a little bit more, Encik Ashraf. Now we are open for Q&A. Probably let me start first. I think that quite often in the in actual environments, you do not always have the complete set of the data set. I don't know if that was being experienced during these projects, and if you could share how do you actually overcome these challenges.
Okay. You can hear me, right?
Yes, I can hear you well.
Okay. So thank you. You are very right. In this real environment, there are a lot of missing data. So I guess we had the luxury of doing it at a real environment. You have years of data. Some of them like taken every hour or even every second, but some of them like lab, they have certain intervals. And like you said, there are also some missing data. Critical, and unfortunately, there are two ways of doing that. Predict, kind of like extrapolate point, but that also come with some cons. If you are confident with it, as a team, we decided to go. Sometimes you also need to decide, could it really predict it, especially when you are testing sub during your plant test run. So yeah, there could be two ways. Depends on it's very unique to the condition plant and things like that. If you want, you decided you cannot really use any data from that point of time.
I see. Thank you very much. I think that one last questions before is that we have a question asking that you have used machine learnings in this particular case, but then there's a recent suggestions on deep learnings. Do you have any plans, or are you working to use deep learning algorithms for the same applications?
I'm not sure when you mention about deep learning, you mean like of algorithm, or because what we decided, because it was just like very like a test run.
I see.
because when we mentioned machine learning, when not so many people knows, especially at the refinery. So we decided just to test with something that very popular at that time, which was new AN and artificial neural network, and this one another SGB. So maybe in the future that could be something that we could look into deep learning algorithm.
Yeah, yeah. I just want to make the point that if you ever considers, I think that UTP we have some of the expertise in the areas of deep learning, so we can always partner together. So I think that the time is up. I think that thank you very much, Ashraf. Very very interesting topics and sharings of your work. We really grateful for that. Thank you for your talk. So
Having me here.
yeah, thank you. So moving on, we have Alish Ba from UTPs to share her work on fractional stochastics gradients descent based learning algorithms for multi-layers MLP neural networks. I think we can go for the next speakers, please.
Hello all, my name is Icias Ps1 and I am from University Technology Petronas, Malaysia. The title of my paper is Fractional Stochastic Gradient Descent Based Learning Algorithm for Multi-Layer Perceptron Neural Network. The table of contents are as follows: abstract, introduction, motivation, our contribution, methodology. In the methodology section, I'll be discussing the dataset, feature selection algorithm, fractional calculus-based MLP architecture, then coming towards the simulation results and conclusion. So this is the abstract of my paper. Neural networks are indispensable tools in adaptive signal processing. Multi-layer perceptron neural network is one of the most widely used neural network architecture. The performance is highly subjective to the optimization of learning parameters. In this study, we propose a learning algorithm for the training of MLP models. Conventionally, backpropagation learning algorithm, also termed as BPMLP, is used. It is a type of stochastic gradient descent-based algorithm where performance is governed by eigenspread of the input-signal correlation matrix. In order to accelerate the performance, we design a combination of integral and fractional gradient terms. The proposed fractional backpropagation multi-layer perceptron method is based on fractional calculus, and it utilizes the concept of fractional power gradient, which provides complementary information about the cost function that helps in rapid conversion. For the validation of our claim, we implemented leukemia cancer classification task and compared our method with the standard BPMLP method. The proposed FBPMLP method, which is based on fractional calculus, outperformed the conventional BPMLP algorithm both in terms of convergence rate and testing accuracy. Coming towards the introduction section, machine learning is becoming an indispensable tool in signal processing domain. Multi-layer perceptron is categorized as an artificial neural network. MLP consists of several layers composed of neurons and their connections. It uses backpropagation algorithm for training the network and can distinguish the data that is non-linearly separable. Its application can be seen in the field of artificial intelligence such as speech recognition, adaptive control systems, communication, robotics, etc. And it is also being applied in healthcare, medical diagnosis applications, language modeling, etc. So, in this paper, we showed the leukemia cancer classification. It is a type of cancer found in your blood and bone marrow, and it is basically caused by the rapid production of abnormal white blood cells. These abnormal white blood cells are not able to fight infection and impair the ability of the bone marrow to produce red blood cells and platelets. So, there are four broad classifications of leukemia. The first one is the acute lymphocytic leukemia, which is known as ALL, acute myelogenous leukemia, AML, chronic lymphocytic leukemia, CLL, and chronic myelogenous leukemia, CML. We have done binary classification in this paper by making use of ALL and AML classification. So, motivation. The conventional derivative takes a tangent data point for the function, while the advanced derivative method gives further information. That is why we used fractional calculus in our study. Recently, fractional calculus-based techniques has been applied in a variety of research areas such as biomedical applications, control engineering, recurrent neural network, etc. So, considering the advancement of fractional calculus-based gradient descent methods, it is interesting to apply the concept for the pattern classification problem. So here comes our contribution. We designed a combination of integral and fractional gradient terms in order to accelerate the performance of the conventional backpropagation learning algorithm for the training of multi-layer perceptron models. In particular, we use the convex combination of the conventional and the fractional stochastic gradient descent method. We also removed the gamma function to reduce the computational complexity. We implemented leukemia cancer classification task and compared our method with the standard BPMLP method. The proposed method, fractional backpropagation multi-layer perceptron, outperformed the conventional BPMLP algorithm. So this is the flow. An input signal in the form of leukemia classification. So there are two classes, ALL and AML. Then we selected the features. Actually, there were 7,129 microgene array. So we selected only 5 genes using minimum redundancy and maximum relevancy algorithm. And then our architecture, and it gives the output. So here is the description of the data set. It consists of 2 classes. As I mentioned before, we are doing binary classification problem. So acute lymphocytic leukemia and acute myelocytic leukemia. So I have divided my data set into training and testing samples. So for training, I selected 27 ALL samples and 11 AML samples. And same for testing, I have selected 20 ALL samples and 14 AML samples. So for the feature selection algorithm, actually there were 7,129 genes in the dataset, and most of the genes either provide no information about the class label or provide redundant information. So to select the most significant genes, the minimum redundancy and maximum relevance technique was used. And it is a powerful tool to extract the most significant information and least redundant data. We managed to reduce the number of attributes from 7,129 to just 5 genes. So this is the architecture of our proposed method. It consists of 3 layers: the input layer, hidden layer, and the output layer. Input layer consists of 5 inputs. Hidden layer consists of 20 neurons, and the final layer output, which is the output layer, consists of a single neuron. So these are the simulation results. The training accuracy achieved by the conventional method, which was the backpropagation multi-layer perceptron algorithm, is 100% at 7th iteration, while the proposed method achieved this 100% accuracy at 3rd iteration, demonstrating the usefulness of the proposed method in terms of speed. Also, the highest testing accuracy is achieved by the proposed method, that is 94.11%. On the other hand, BPMLP achieved the highest accuracy of 91.17%, which is almost 2.94% lesser as compared to the proposed method. Coming towards the conclusion section, a novel FBPMLP algorithm is proposed in this research. The proposed method uses the fractional gradient descent and the conventional least mean square algorithm, adopting the characteristics of both. The FBPMLP method efficiently learns the optimum weights, and it is investigated for the leukemia classification problem. The proposed method also compared with the conventional BPMLP algorithm, and it outperformed the conventional BPMLP algorithm by achieving the highest accuracy of 94.11%. Thank you.
Okay, thanks, Alishba. Thanks for the nice presentations.
Thank you.
If I can ask you, some questions
Yeah.
on behalf of the audience. I think that you mentioned that you selected eventually after you filtering out, you have 5 main genes that you're looking at and feeding into the MLP. Why is Question is, why is it 5? And also, if you were to include more genes, would you expect that the improvement in terms of your accuracy?
Actually, I have selected 5 genes. Based on that, the accuracy was relatively high. So that is why I selected 5 genes. And basically, the idea behind using MRMR algorithm is that it takes those features which are like mutually different from each other. So that is why I selected those, and it actually eliminates the redundant information. There are features available, so they are highly correlated. So that is why, yeah, we can try taking um, more genes. In my case, I have used 5, but I ran some experiments taking more genes, but it was not improving the accuracy. So that is why I choose this number, like 5 in my case.
I see. Okay, thanks. Have you tried that? I see that in your MLPs, you are just using a single layer, a single hidden layers. Have
Yeah.
you tried more than one hidden layers to improve the modeling abilities?
No, because in my case, actually, the conventional benchmark approaches do not offer better accuracy, and obviously the convergence rate also. If I increase the number of layers or the number of neurons, it will increase the convergence rate or the speed of the system. So that is why, yeah, we can try in this era also to increase the number of neurons or layers, or we can go to the deep learning side.
I see.
Yeah.
Uh, okay, it's just me asking. I think that the other one, I think that is quite similar to the previous talk as well. I think that nowadays, I believe that you also working on deep learnings,
Yeah. Yeah.
and I think the data set would it be large enough for you to actually to throw it in for the deep learnings and
Exactly.
actually to look for the bigger, better improvements. Yeah.
Mm-hmm. Yeah, that is actually basically this paper has been written like 1.5 year ago, and now actually my direction has been shifted towards the other side also. So that is why I have not been planning to doing the deep learning task on it. So yeah, just achieved a good accuracy so
Mhm.
with this.
Okay. It's just that in the current case that you're using the MLP is based on the binary classification, so two types, isn't it? Yeah.
Yeah, yeah, ALL and AML, only two types.
Mm. Is there subtypes of, in terms of the severities that it has been labeled with the data sets, or they are just being labeled into these two
Oh
classes?
no, they are just being labeled like ALL, labeled like class one and not subcategories.
I see. I see. Okay. I think that. I think that if the audience, if you all have any questions, do post it. I think that Alishba also can answer you at the later stage. We will share with all the presenters all the questions if there's any. Otherwise, I thank Alishba again. Wonderful talks, very interesting. Thank you, Alishba.
Thank you so much.
Thank you. So moving on, I think that before I introduce the next speakers, I think that just to remind the participants that actually it is possible for you to actually enlarge the screens, if I'm not wrong, to actually to have a clear views of the presentation itself. Okay. So thanks, Alishba. So I'll proceed with the next talk. Next, we will have Noaina, also from UTPs. She will be sharing with us on her topics on breast cancer detections by hybrid techniques based on deep learning network. So
after lung cancer. So the current diagnosis method consists of two types, which are screening mammograms and diagnostic mammograms. So screening mammograms. Assalamualaikum and greetings. I bid to everyone. I'm Aina and today I'm going to present my research titled Breast Cancer Detection by Hybrid Techniques based on Deep Learning Networks. So breast cancer refers to the presence of abnormalities in human breast tissue. It's a second disease that significantly harms a human life globally after lung cancer. So the current diagnosis method consists of two types, which are screening mammograms and diagnostic mammograms. So screening mammograms are the first type of an X-ray examination to detect the presence of cancer. If abnormalities detected from screening mammograms, the patient need to proceed to the next step, which is diagnostic mammography. So diagnostic mammography is a more complex phase compared to the screening mammograms, as it aims to precisely detect the location of abnormal masses, know its size, and determining the tumor's class, whether it's benign or malignant. So double reading methods introduced to reduce the false positive rates in a single reading mammograms. So double reading involves with two radiologists examine on the same one mammogram image at the same time. So this method does improve the accuracy detection, but at the same time it increases the cost and more time consuming. Besides, the challenge faced by radiologists in precisely locate the cancerous cells are poor quality of mammogram image, lack of expert radiologists, and loss of data to be interpreted in a limited time. So the main objective of this research is to develop a second reader system to ease the radiologist's workloads, where it can be achieved with the following sub-objectives, which are to develop a computer-aided analysis CAD system that could automatically detect the breast cancer. And the second one is to analyze the proposed system effectiveness by comparative study with previous related work. So two publicly available mammography datasets were utilized in this research, which are MAIAS and DDSM. However, as we can see from table 1, both sources of the dataset were not provided with the same dimension. Therefore, for a standardized dimension of image, raw image were reduced to a small size of 448 pixels, which contribute to a faster computation for the subsequent process. So in this work, 400 images were randomly chosen from each dataset, where the selected image were augmented by 4 times to increase the learning rate. So for preprocessing operation, suitability on applying nose filtration method is crucial to reduce the information loss. So table 2 shows the evaluation on different types of filtering methods applied to the same mammogram image together with the respective mean square error value. So mean square error or MSE is the average of the square difference between the original and the predicted image. So the lower the value in MSE, the better the quality of the image produced. So referring to this table, 3.3 times 3 window filters show the lowest value of MSE. Therefore, this filter was adopted as a noise removal filter in this algorithm. To increase the contrast between normal and abnormal tissue, the noise remove image was enhanced by using a top and bottom filtering methods. Next, for the purpose of getting a better results, the preprocessed image was filtered further by a loss mask to remove the secondary features, which may reduce the classification performance later. So this is the process flow for the segmentation operation. For the loss mask part, we can see that from the third image that applying the loss mask gives advantages in segregating the bacterial masses from the breast tissue, which brings benefit for the active contour to deform to the RI boundary on the binary image. So the deformation of active contour occurs by placing a rectangle initial image on the loss mask filtered image. So the mask will deform based on the image force, which leads the mask to move toward the object boundary. So green line here refers to the movement of the active contours mask and subsequently produce the segmented image. So the RI in this research will be the breast area. So for the future accession stage, 3 pre-trained network, which are LSNet, XNet50, and accession LSNet V2 were studied based on their validation accuracy and loss percentage. Among those 3 pre-trained networks, accession LSNet V2 shows the highest accuracy, which demonstrates its capability in learning the image features effectively. Therefore, it was adopted as a feature extraction in this algorithm. So 1,000 features were extracted in total and reduced via principal component analysis (PCA) to save the computational time and to reduce the possibility of overfit. So PCA works by finding the most common factors of the features and rank them to their importance. Therefore, only the top selected features were considered and transferred to the classifier via transfer learning operation. So SVM has been chosen as a classifier due to its capability in producing significant accuracy with less computation power. In this process, all the SVM tasks of classifier were studied to identify the best SVM model in classifying the normal and abnormal image. So 10 full cross-validation was applied where all the datasets were randomly chosen and divided equally into 10 subsets. So 9 subsets were used as a training set, while the remaining 1 subset was utilized as a testing datasets. So cross-validation is essential in ensuring that every mammography image was not placed in a test set repeatedly to reduce the bias error. So the result shown in table 3 indicates that the QPSVN demonstrates the highest performance with 97.50% accuracy. Therefore, QPSVM was utilized as a classifier in its algorithm. So full computational assessment was utilized to evaluate the system performance, which are the accuracy, sensitivity, specificity, and area under curve, or OUC. So TP refers to true positive, where it shows the correctly classified abnormal image as abnormal. TN or true negative refers to the situation where the normal image is correctly classified as normal. Meanwhile, the FP or false positive happen where incorrectly classified normal image as abnormal. And FN is a situation where the system incorrectly classifies abnormal image as normal. So ROC is the abbreviation for the receiver operating characteristic curve, which is commonly used as an evaluator for the classification model purpose. So in general, higher accuracy indicates better performance of the classifier. So the purpose algorithm managed to attain competitive results with 97.50% accuracy, 96.67% sensitivity, and 98.33% specificity. Note that the SL model has an AUC near to 1, meanwhile the AUC below 0.5 shows the model has a low measure of superability. So through the plotted curve, it shows that the proposed system is reliable to be used as a corridor as it attained the AUC up to 0.99. So several work have been done by other researchers to study the effectiveness of the loose mass as a secondary feature remover. So a performance comparison between the proposed algorithm with previous related works were tabulated as in table 4. So through analyzation, breast cancer detection algorithm proposed by reference 11 attained the highest detection accuracy of 97.91%, which is slightly higher than the proposed method. However, they only use 61 image, which is lower than our method, where they use 21 image for training and 40 image for testing. So based on the analysis of research findings, it can be concluded that the proposed automatic system was able to detect the abnormalities present in mammography with 97.50% accuracy, 96.67% sensitivity, 98.33% specificity, and 0.99 AUC. So besides, the system was feasible to be considered as a second reader as the computational time for the system to train took about 7 minutes and 48 seconds, and validation about 7 minutes and 11 seconds only. That's all from me. Thank you for listening.
Right. Thanks, Aina. Are you there? Aina, are you there?
Hello, can you hear me?
Yeah. Now I can hear you. Yeah.
Sorry, I forgot to press okay. Okay.
Okay, that's good. That's good. Now people can see. Right. Okay. So let me start with. I think that I guess that because of the time constraints, that's why you have not gone through great details. But can you share with us on how did you choose the models? You know, this particular deep learning models for these applications. I mean, there are a lots of from the literatures we have a very rich varieties of. How did you select on these particular models?
Okay. When I'm doing that paper,
those three printer network that I have tried so far. So I write that paper up and display. But then after I submit, then I realized that this question might be asked. So I've tried run all the other printer network already, and it shows that it's HRSnet V2 still the highest one.
I think that what are the features of these particular models that actually provide the superior performance? Can you share with us so that our audience probably can learn from that?
Basically from deep learning, firstly, the features that they extract is the basic one first, the age, the color, and intensity, that so on. And after that, it will go in deeper and deeper. And when it's getting more complex, then depends on each layer.
How do you decide on how deep the layers it should be?
How deep the layers?
Yeah.
Uh,
Many people talk about deep learnings, right? So deeper the layers, then you can extract more different. But
uh,
how do you decide that, if you can share?
I just run one by one because the one that I know is if it's overly extracted, the accuracy will be low. And then I choose compare between those and choose the highest accuracy between them. So I know that it's suitable. The deep is suitable for that network.
I see. Okay. So okay. So you have very impressive results. 97% and so on. Can you share where's the missing 2% on? Where are the failing 2% coming from? And if you have you done any analysis on that?
Usually, the fault will become to the uh, incapability to remove the second feature spectral muscles. So because cancer tends to have a highest intensity, but pectoralis muscle also has the same highest intensity. So some of the image were unable to remove that. So I think so that is one of the image that contribute to the loss.
Mm. So if someone would like to extend your current work, what would you recommend?
Um, I think it's better to because now the I think it's better to propose properly try another uh, to improve the segmentation because now the segmentation is not quite good. Still has the loss. So I think if we improve the segmentation part, it will improve the classification accuracy as well.
I see. So okay, so you did the comparisons between having a ROI being segmented out and versus actually viewing it from the raw signals, at the large signal. So superior results coming from after to do the segmentations. But then there's still some elements in the accuracy in terms of segmentations that actually restricts for you to achieving 100%. Yeah.
Yeah.
Okay. Right. I think that if no further questions, I think that if you have any if you have any other questions, that you want to put forward to Aina to answers, please put in there's a button below on the live Q&A. You can post your questions, then we will try to answer later on. Uh, if no further question at this point, we thanks Aina for a very interesting talks. Thank you for
Okay.
thank you.
Okay. Thank you.
Okay. Now, moving on to the next speakers, we have Ahmad Bukhari coming from UTPs. He will be presenting his work on DL nets with convolutional neural networks. I think that just to remind you again that there's options to actually to enlarge the screens to actually to see the presentation clearly. Now, I think so, and also we look forward for your questions for all the speakers. We have all the speakers here with us today, and so that this is a wonderful chance for you to actually raise any questions that how that what they have done might relates to your work itself. So without further ado, can we proceed to the next speakers? Bukhari, please.
Assalamualaikum warahmatullahi taala wabarakatuh. My name is Ahmad Bukhari bin Audi. I'm from Ministry of Technology Petronas Malaysia, and today I'm going to present my work entitled The ANET with Convolution Neural Network. As an introduction, automated robotic autonomous screening and diagnosis using deep learning model based on convolution neural network had been previously developed to help first facing word blogging prevalence of DR, and second to alleviate ophthalmologist's burden to analyze funded images for presence of DR. Previous work by Gaussian, Racklin, Boyes are basically re-implementing or with little improvisation of previously proposed CNN architecture without carefully selecting and choosing the right model hyperparameter. CNN model hyperparameter like depth and channel scaling factor which determine network structure is very important since it directly controls the behavior of the training algorithm, hence having a significant impact on the performance of the model itself. And hence we argue that it is very important for us to categorize the effect of the ANET depth and channel scaling factor to better select a best network for the purpose of full-body detection application. So, the purpose of this study is to characterize and understand the effect of different DNS channel scaling factor, network depth over its predictive performance to predict the presence of the full-body on fundus image. So, we pose the question, what is the AUC of ROC, or area under the curve of receivable operating curve profile of different DNS channel scaling factor and depth, as well as the best channel scaling factor and depth configuration to detect the presence of the full-body from fundus image. So we hypothesize that this channel scaling factor be denoted as an E ratio and network depth denoted as a D over X control the numbers of parameters which is measured in multiplied at computation or MAC in a given network layers. This changes its model parameters number, i.e. MAC, will directly affect model's representation, learning capability, or the predictive performance itself. So, we aim to answer the research question, we pose these three research objectives. First one is to develop CNN-based DNet that have channel scaling factor E ratio with a changeable depth dx. Secondly, we pose to investigate DNet predictive performance measured in AUC over different channel scaling factor E ratio and depth dx value measured in MAC. Thirdly, we will compare the best DNet channel scaling factor and depth configuration against previous works. The contribution of this paper are as follows. First, we provide an understanding of the DNet's predictive performance profile of a different configuration of DNet channel scaling factor, E ratio, and depth dx. Hence, in turn, reduce the number of DNet's free parameters itself. And a DNet with reduced number of parameters will decrease its complexity and thus enabling us for future mobile deployment application. Here is our proposed network architecture. We have here figure 1 is a two different kind of convolution. First, pointwise convolution with 1/1 plus n kernel. Second, a convolution with k by k times k times n kernel. And then we have our own the ANET module here, where information going into a scale up and down pointwise convolution, okay, and denoted as an E ratio here. And then we have a convolution 3 by 3 before it goes out to the right. And then based on the ANET module, we combine to develop the ANET blocks with a skip connection. And each ANET module is followed by base normalization BN and value activation before it add into the previous network, previous information, and then feed to a value activation and then out to down here. And on the right is a complete ANET architecture with input 3 400 by 400. These are image input of the ANET, and then through a series of transformation, and output will have a 2 output. It's either referable or non-referable DR. In addition, we present the implementation details that we use in this study. For optimizer or learner, we use Adam optimizer with learner rate 0.01. We use base size of 64. We develop our ANET architecture based on PyTorch library. We do the training and inference on 4 NVIDIA V100 GPU. For the dataset, we use 2 kinds of dataset. First is DR Kaggle. Second is Messidor 2. We use DR Kaggle as a training set, consists of 88,000, and then we use Messidor 2 as our testing set, it consists of 1,700. On the left, this is example of preprocessing that we use using normalized estimated background using local average color on each image color channel. We do this in order to standardize the representation of DR images. As you can see on the left here, you have a very clean image on the top here, but down here, very blurred images. After preprocessing, we have a quite standardized representation. For experimentation, we have 2 channel scaling factor E ratio and 3 depth value. So in total, we have 6 different architecture that can be produced. We name it as a H1, H2, up to H3. We did some comparative analysis between these 6 architecture based on AUC and MAC measures. And we also did some comparative analysis between best architecture, H-best, and we will study based on AUC, sensitivity, and specificity measures. These are the results of all the architectures performance, AUC versus MACs. On the left is a bar chart of a scaling factor E ratio equal to 0.05. On the right, we have a scaling factor E ratio equal to 1. For each axis represents the MAC value, so with different depth. So you have here 3 configuration of depth. Down here, for E ratio equal to 1, also we have 3 different depth. For E ratio equal to 0.5, all the network depth configuration is hardly good in terms of operating performance. All are below 0.6 AUC. For scaling factor E ratio equal to 1, as you can see here, there are 2 networks with MAC 2.89 and MAC 6.24, having quite good operating performance compared with the higher MAC, 9.56. So based on this performance, we select H4 due to it has the lowest numbers of MACs. Or you can say that it has the less complex compared with others, compared with H5. On the right, we have a table 2, is a result of previous work compared with our best network. We have a 0.96, which is comparable with other DNet previously proposed. As a conclusion, we developed a CNN-based DNet architecture and study the effect of channel scaling factor E ratio and depth onto its predictive performance. However, having the channel scaling factor E ratio equal to 0.5 causes the network to perform badly, whereby all the configurations are having AUC less than 0.6. DNet with MAC DNet H4 with MAC 2.89 G and MAC network for network H5 with MAC 6.24 are having almost the same predictive performance, which are equivalent to AUC 0.96. However, we chose H4 as our H-best due to the fact that it has the lowest MAC value. The predictive performance AUC of H-best is comparable with previous work. That's all my presentation. Thank you.
Right. Thanks, Bukhari, for very interesting talks. Just probably the sound is a bit on the weak side. Right. Now we are open for question and answers if there's any. Thank you. Let me start first. I think that nowadays the deep learnings has a very strong, how to say, modern abilities, and we want to maximize the amounts of informations to be presented to it, right? And people in the past, we have been traditionals for machine learning and so on. We tend to do a lot of pre-processing so that it makes the life easy for the machine learnings just to pick up the core informations. Now, with the introductions of deep learning models and so on, have you tried to look at, what if you don't do even any pre-processing and just try to fit it in? How that would affect the performance, and could you comment on that? Thank you.
Thank you, Dr. Tang. First of all, if my audio is okay?
I think that you have to speak a bit louder, so we can't hear you.
Hello? How about now?
Still a bit quite weak, your sound. Mm.
Hello? Hello? How about now?
It's still a bit weak. I can't hear you at all. Yeah. Unfortunately, I can't hear any sounds coming from Gary's side. Can you use the machines directly on the voice, or can you select on other input for your audios itself?
How about now?
Yeah, this is good.
Oh, okay.
Yeah.
Okay. The question just now about pre-processing, comparison with machine learning and deep learning. Previous work on machine learning, they require pre-processing in order to make the features linearly separable. So after you have all these features linearly separable, it's easier for the classifier to do and to learn the classification or the classifier model. For deep learning, I haven't seen so much work on preprocessing. Probably the nature of deep learning itself that can learn or that can learn a high complex features and extract high dimensional features directly given a data set which probably with noise inside. And in fact, there's some work that have been done and focused on using deep learning to do noise removable. So I believe that there is a strength in the deep learning in the structure of convolution neural network that work on to remove the noise on the data. Probably, I think that if we include preprocessing within our within the deep learning methodology itself, probably it might help. How much? I'm not sure.
Okay, thanks for the comments, Bukhari. I think thanks again for your presentations. So I think that we will move on to the next speakers. Thank you.
Thank you, Dr.
Okay, so next we have Nivesh from UTPs. He will be sharing on his work related to analysis of unsupervised loss functions for homography estimations. Without further ado, let's have Nivesh.
The images using some kind of Gaussian noises, or we then rotate the images with Good morning, everyone. My name is Nivesh Vedpudi. I'm a PhD student at University Technology Petronas, Malaysia. So my topic for today's conference presentation is analysis of unsupervised loss function for homography estimation. So moving on to the first slide, you can see the contents of this presentation further. So that is introduction. Then we will see like what are the loss functions used for supervised homography estimation. Then the loss functions for unsupervised homography estimation, and what are the architectures of neural networks that are being used for these both kind of different techniques like supervised and unsupervised, and the methodology that we followed for this current conference presentation, or like the research what we did, and finally we conclude with our experiments and results. Coming to introduction, if you ask me what is homography, it is a process of estimating the transformation between two images, assuming there is the both images are having the planar scene assumption. It means that there is no motion parallax or anything like that. So the major applications of homography is visual SLAM or visual OO, like visual odometry or structure from motion. So before going to in detail about like homography, I just wanted to conclude it with what are the types of some few types of the image transformations, and I have presented three different types of image transformations on the presentation slide here. So the first one is similarity, the second one is FN, and the third one is homography. So similarity is concerned about only the translation, rotation, and scaling effects between two images. But coming to the FN transformations, it is a 6 degrees of freedom of transformation, which takes translation, rotation, scale, shear, and aspect ratio into the account. So homography is a transformation that is related to 8 degrees of motion. So it takes into account the translation, scale, shear, and aspect ratio that's being taken care of FN, plus distortions in the images. So coming going further to the into the introduction, so you can see like deep learning methods or like machine learning methods, or traditionally classified into two types, like one is supervised and the other one is unsupervised. So you can see a kind of conclusion tabulation here, like between two techniques. One is machine learning and deep learning. Then we have different types of in supervised and different types in unsupervised. So that's what being like kind of concluded in this table. So that is regression, classification, and clustering. So you can have a look at all the techniques what we are using from so long. So the basic difference between supervised and unsupervised is supervised learning needs a ground truth data, but unsupervised learning doesn't need any kind of ground truth data. So in my research area, what I mean by ground truth data means it might be the Euler angles or the quaternions, which tells about the transformation between two images, like 3 degrees of translation and 3 degrees of rotation. So we are actually measuring the transformation of the camera from one point to the second point with respect to time. So coming to the loss functions for supervised homography estimation. So like supervised homography estimations, like in the literature, there are researchers used two ways of solving this problem, one by regression and the other one by classification. Though the classification proved to be less effective, and most of the research currently nowadays they are using only in the form of regression. So coming to different losses that are being used in regression, that is mean squared error or mean absolute error. Those are the de facto losses used for regression or any kind of continuous variable error metrics. And in terms of classification, we have cross entropy, like categorical cross entropy and sparse categorical cross entropy loss. So the loss function is like considered as the heart of the any kind of optimization algorithm, because that is what drives us to the optimal values of the like parameters or the networks or something. So going to the unsupervised homography estimation. In unsupervised homography estimation, the loss functions are used, like there are different loss functions used. One is L1 loss, or like mean absolute error, like that is almost similar to mean absolute error, and L2 loss, which is almost like kind of similar to mean squared error. And the third aspect is the third loss function that is used in unsupervised homography estimation is textual similarity index. So this textual similarity index takes like considers the distribution of the image. I mean, like it takes the distribution of the image in like different aspects, like luminance, contrast, and texture. So unlike we are calculating a one-to-one value here, we are calculating two images. Like one is a input image, and the other one is a reconstructed image. So these two images should be almost similar. The network totally concentrates on minimizing the error between these two images. So like the parameters, the gradients flow backward, and the parameters are adjusted in order for us to like kind of bring the reconstructed image close to the input image. So that is how unsupervised homography estimation is worked out. So coming to the architectures that are being proposed, and like some of the initial architectures that are being proposed in supervised and unsupervised learning, or like one is a homography net and the other one is the unsupervised homography net. So as I've already told, the deep homography net like outputs 8 values of the homography matrix. So in general, this is a a homography is a 3 by 3 matrix with 9 elements in it. So the one element of all those 9 elements is for the scaling of the transformation. So we are not predicting that one, but we are concerned about the 8 degrees of freedom that we have mentioned before. So you can see that it outputs 8 values. So we directly use any kind of error metrics like mean squared error or mean absolute error for this aspect. In terms of unsupervised homography net, we use the homography net, but we use it in an end-to-end fashion. So what does it mean by end-to-end fashion? We have a lot of components that are interconnected as a same network. So it works as a same network, and you can see here, we are inputting the image T, and then we get the homography output in the intermediate stages, and that homography is transferred to direct linear transformer. There you get the transformation of the images, like rotations and transformations. From there, we use spatial transformer networks. That's a research published by Google Mind. So what we do is we take the like image t, like image at time t, and we take the transformations, and we are trying to reproject the same image uh, with the transformations in different image plane. So that is the reconstruction that is being done. So coming to the methodology, we are focused on, like, mainly focused on what is a better loss function in terms of like reconstructing an image. Like what is a different, like which loss can actually differentiate much better when compared to others, because we have some criteria that we'll be discussing later. So you can see that the first one is like we take an image, then convert into RGB to grayscale, that is red, green, blue to grayscale. Then we normalize it, and then we kind of augment the images using some kind of Gaussian noises, or like we then rotate the images with like the known rotation pairs, and then we calculate the losses between the augmented image and the standard input image. So coming to the experimentation results, you can see like I'm sorry. So there are different examples of augmented images that are being displayed on the presentation slide. So in the first row, that is we are concerned only about adding the noises. So you can see that sigma, that is a standard deviation. The not like standard deviation of the noise that is being added. So in the like A, that is pure image. B, we added 0.05 of sigma, and then C. So we increased in that level. So, and in the second row, you can see that the images are augmented based on the rotations. And in the third row, you can see that images are augmented based on the exposure value, right? So coming to the experimentation and results, you can see that three different graphs are being displayed on the screen. So the first one is with respect to the noise, and the second one is with respect to exposure, and the third one is with respect to rotation. So you can see like the graphs, like one is different, like L1 loss is different from L2 loss, but what we wanted to conclude is, like the ideal loss function for any kind of task that calculates the transformation between images using reconstructed images. We expect the ideal loss to be resistant to noise. I mean, like, even though there is a little bit of noise or illumination changes. So because the illumination changes is like you can drive an autonomous car in the morning or in the evening time, so that the structure of the like the environment is same in the morning and the evening, but the illumination changes, the lighting changes, so the illumination changes. So we want our loss function to be resistant to noise and illumination, but at the same time it should be sensitive to geometric transformation. So when I tell geometric transformations, it's about the rotation of the images. So you can see that L1 performed very well in terms of rotation and noise images, right? So the L1 loss is higher in terms of rotation images. That means when there is a rotation, our loss function is focusing much on the L1 loss is focusing much on the rotations, but L2 loss is less sensitive to L1 when compared to the rotations. But on the other hand, when we come to the noise, addition of noise, L1 loss is less sensitive. I mean, like I told that we expect our loss to be less sensitive to noise and the exposure value. So you can see that L1 is less sensitive when compared with exposure variation and the noise variations. So in conclusion, we in our future works, like in our current works, we are actually using L1 loss, then L2 loss. That L2 loss is being used in a lot of researchers, used by a lot of researchers, but there isn't a kind of documented evidence that L1 is better than L2. So we are performing our current experimentation with L1 loss, and we are getting a considerably good results when when compared with L2 in terms of whole end-to-end fashion. So That's it for this conference presentation, and thank you very much for your kind patience, and thank you for being here with me. Thank you very much.
Thank you, Nivesh. Thank you. So I think that with the time, I think that we only have probably have time for one questions. Okay, I have one question.
Yes, sir. Sure.
Uh, I think that noise has been exploited in communications when trying to maximize information transfer. So in terms of the entropies, that is quite commonly used in communications.
Yes.
But then I see that, however, looking at your results, seems that when I start to increase further the noise, it actually the loss actually increases as well. Uh, I wonder if you can look at the lower end of the spectrum. Maybe I'm wondering if you are looking at too high amplitudes. That's why you are seeing with the injections of noise actually cause more losses of informations. If you start to reduce at the lower levels, small injections, perhaps that would actually improve. Any comments on that? Thank you.
Actually, in terms of noise addition between two consecutive images, what happens is like the L1 loss is a squared loss. So even a small, minute, like kind of variation, it kind of spikes up. I mean, like it increases the loss. So what happens? The loss increases when there is a noise, and we are not concerned about the noise in terms of geometric transformations. We are only concerned about the rotations and like translations of the images. For suppose we can take like I'm sorry. So for suppose we took one image here, and like again we took second image at some time frame. So, like from the viewpoint of the camera, you can see all the features. Some of them are like overlapping and some of them are not. So we are only concerned about the three-dimensional structure in between two images. So when there is a noise and when the loss function increases, like in the like gradient descent, the parameters also adjust proportionally to the increase in the loss function. So this is a kind of preliminary analysis where it's actually telling that for this study, yes, of course, I agree with you that in terms of data transfer, they use this noise as like main key for entropy and thing. But in terms of this application, I think like the noise, because when we have a camera in front of our car and when we are driving for 10 meters, like the exposure changes, there might be some kind of blur or like additional noise that is being induced, but the three-dimensional structure beneath, like inside the frame, it always remains the same. So whatever the loss we are using, that shouldn't like kind of change much with the with what isn't necessary for the network. I mean, like for example, noise or the for illumination, but it should be very sensitive in terms of rotations and translations. So what I am guessing is like my kind of analysis is like the small noises or the small Gaussian, like the salt and pepper noise or anything. So the small thing that's like kind of as L2 is a squared loss, so it's kind of uh, the variation is much higher when compared with the absolute difference. So I mean, like, and at the same time, that square difference is not is helping a lot in terms of rotations when there are rotations or transformations. But the absolute difference is not helping at all in terms of transformation. So that is what we concern. I mean, like, there are two things what we have to carefully weight here. One is noise and the exposure. We have to weight low, and at the same time, the rotations and the transformation should be higher. I mean, like the importance should be higher. So in that view, L2 is performing very well when compared with the L1 for this specific application.
Okay, thanks for very clear explanations, Nivesh. Thanks again for your wonderful talks. Thank you for sharing us your work. Thank you.
Thank you, sir. Thank you very much, sir.
Okay. So now we move on to our next speakers, Dr. Mohammed, who will be sharing with us on his work on crowd analysis of a masjid Nabawi using CNN of TV's footage. Please welcome Dr. Mohammed.
Is to convert these predictions or number predictions into an actual live tracking movement of. Hello, welcome to the crowd analysis of Al-Masjid al-Nabawi using convolutional neural networks of CCTV footage. My name is Mohammed Abdulal. I'm an assistant professor at the Department of Electrical and Computer Engineering at King Abdulaziz University. I'm also a member of the Center of Excellence in Intelligent Engineering Systems. Overcrowding and Hajj. In 2015, accidents happened that caused more than 700 pilgrims to die. Before that, in 2006, 363 people died also at Hajj due to overcrowding. Due to these accidents, the Ministry of Municipal and Rural Affairs have initiated many programs to better monitor and control the flow of pilgrims during Al-Hajj. Many improvements have been since then, and this is an attempt to contribute to these efforts. Moreover, in the pandemic, the need for crowd management has increased due to the fear of exposure to contagious viruses. There are various technologies that can be used to estimate crowd movement and management, help with crowd management inside of large areas. For example, the use of head count at entrances and exits can be used to know the exact number of people inside the building by knowing the number of people entering and the number of people who have left. However, this doesn't tell you where people inside the building are, and it doesn't tell you where they are moving towards or moving from a point. So therefore, although this technology is very cheap, however, it does not help with the actual overcrowding in specific areas inside of large areas. Another technology which is used is the use of radio frequency identification, RFID. This technology uses small towers or sometimes larger towers distributed around a large area where each person has a tag or a transmitter that will transmit its ID to the tower, and the receiver at the towers will then accumulate all of the data from everyone, and then they will know the location of each one individually. Knowing that will tell you where the movement is happening and where the flow of each tag or person is going. Therefore, it's a very accurate technology that could help with the crowd management and the flow of people. This technology is also used with safety, security, and even medical and transportation purposes, where it could provide information about the person who's moving and their medical history. The main backdrop with this technology is that it's very costly and it requires heavy infrastructure changing in almost all the corners of the large areas. Other technologies use Wi-Fi or GSM, which is very similar to the RFID. However, it requires no specific infrastructure. It could use existing systems, such as Wi-Fi, where internet broadband is available in some large area, or GSM networks that could provide location and crowd movement inside of the large areas. The main problem is that it requires end user being educated, end user having data plans, and using a smartphone or leaving them on during this experience. And since this system requires contribution from the people, it will have that barrier and obstacle of having to educate the elderly and the children. Other systems have been used to provide crowd management is the use of UAVs imagery. So you have a camera on a drone, and this drone is going to tell you where the crowd areas are. However, this is applicable in large areas and from high distances, and not in small area where you don't know what you cannot see the images from that drone. The proposed solution is to use existing CCTV camera the ones that are already used in heavy places like the Holy Mosque in Mecca and the Masjid al-Nabawi in Medina. These areas are fully equipped with CCTV systems everywhere. So these could help counting the numbers in every single place, in every single corner in the mosque, and this could actually help track the movement in real time. So the proposed solution is to convert these predictions or number predictions into an actual live tracking movement of flow prediction movement inside large buildings such as Al-Masjid al-Nabawi. The methodology is to use density maps for training the neural networks. Density maps are basically pictures where each head is represented by a dot annotation. These annotations are used for training the VGG19 image classification network, which is a very famous, very deep neural network that is used for large-scale images. The loss function was defined by the difference between the ground truth and the estimated or the predicted output. This model was trained using large datasets. There is the UCF-Q&RF dataset, and there is the Shanghai Technology A and B dataset, which contain combined more than 2,500 images. The images were tested on the CCTV camera, and the ground truth values were obtained manually by surveying each area inside the mosque and seeing how many people can fit actually inside a designated area. The occupancy, therefore, was calculated by the predicted current divided by the maximum number, which gives us a percentage. This was done for every single area inside the mosque where the camera was available to take pictures inside the mosque. When there were more than one camera, what was happening was that the average for the overlay of the overlap of the images was taken, and it was presented in the model. There were 19 CCTV scenes inside the mosque, and these were tested within using our system, and it was compared to before and after the pandemic, just to compare the results in the images. The system was tested on 2 different days, one before the pandemic occurred and one during the pandemic. The left side of the slide shows the results of the predictions before the pandemic, while the right side of the slide shows the predictions during the pandemic. The predicted values / the actual head count are shown in the right column in each half of the page. When the middle column of each half of the page shows the predicted outcome of the model. As you can see, the prediction values are pretty close to the actual head counts, and this was done by manually counting the heads of every single person in the picture. This was then used to predict the flow of the movement. The system provides valuable information with no need of any new hardware or infrastructure. It requires no smartphones or data plans for users. And the best of this, it doesn't require educating people. So you need to involve the user experience of the programs inside of the software to be able to define the need and predict the flow. However, this could also be used to gather big data and help predict accidents and overcrowding in the future by using predictive modeling. However, there are limitations caused by high computational power needed for the predictions in real time. In summary, this project aims to provide a low-cost solution to solve the crowd problems using existing infrastructure without basically having to invest in large projects. The inputs was used the density maps to train the VGG19 network models. And then the prediction were used by predefined information about the maximum occupancy that was surveyed annually. These continuous predictions of numbers of the people inside the area can then be used to model the crowd flow of the movement, which was shown in the previous example. Thank you very much for paying attention.
Thank you, speakers, for the wonderful presentations. Really appreciate that. Do I have Dr. Muhammad? Can I connect? I was informed that Dr. Muhammad's internet probably is a bit not so stable.
Hello.
You're here.
Hello. Welcome to the crowd analysis of Al-Masjid al-Nabawi using convolutional neural networks of CCTV footage. My name is Mohammed Abdulal. I'm an assistant professor at the Department of Electrical and Computer Engineering at King Abdulaziz University.
Yes, I think that we only have one. I think that the time is almost up. I think that I just have one question. I think that you have very, very promising solutions over here. And I wonder what would be your next steps to actually make it into a commercial product that are available for the markets. Can you comment on that? Yes.
Yes, thank you very much, Dr. Boon. Thank you very much for having me, and thank you very much for the perfect organization of such a large event. I think the next big step is to gather as much data as we can in order to validate the accuracy, get more depth into the value of the information we can get, because the more data we can get, the more we will be able to achieve better predictions. And once we've figured out what sort of prediction we can get from that, this is where we will transfer them into a commercial or into a very practical solution for many of the other crowded areas within the kingdom and around the world. So yes, it's the next step is the rigor, basically getting the rigor right.
Right. It sounds exciting. I wish you all the best to be able to commercialize it, and we look forward to it. So thanks for spending some time with us to share with us your excellent works today. Thank you.
Thank you very much for your time. Very good organization. Thank you very much.
Thank you. Now, without further ado, we will have our last speakers for today. Let's move on. We have Dr. Saad from UTPs actually presenting either crop or PET, the input volumes. What is the beneficials for CNN? Please welcome Dr. Saad, our last speakers for this session.
Thank you. My name is Saad. Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullah. My name is Saad, and I am representing Center for Intelligent Signal and Imaging Research at UTP. And I'm also representing Center of Excellence in Intelligent Engineering Systems at King Abdulaziz University, Saudi Arabia. My co-authors are Ubaid al-Saggaf, Abdulaziz Buttalab, Mohammed Moinuddin, Sulg al-Faqih, and Tang Tangbun. The title of my presentation is Either Crop or Pad the Input Volume. What is beneficial for CNN? The outline of my presentation is introducing the deep learning in CNN, and then defining the problem, and then presenting the aim of the work, discussing the experiment and the data set, and followed by results and conclusion. CNN is a class of deep learning which proved to be very promising in pattern recognition applications. It attracted attention partially when the large-scale CNN for image classification successfully outperformed all other techniques in the ImageNet 2012 competition. The stunning advantage of CNNs lies in their ability to reliably and automatically extract relevant features instead of manual extraction from high-dimensional dataset, which is highly susceptible to human errors. In the field of computer vision, and in particular image classification, ImageNet has gained a lot of attention. It has more than 1 million images and 1,000 classes of different sizes. The performance improved over the years with deeper CNN layers and matching a superhuman performance in 2015. As we can see that the error has reduced over the years with going deeper and deeper. You can see the error, the layers have gone to 152 in 2015. So why deep learning? Deep learning is very much similar to our visual cortex, visual learning that we do. And the proof that problems which can be represented with a polynomial number of nodes with k layers may require an exponential number of nodes with k minus 1 layers. Highly varying functions can be efficiently represented with deep architectures. Sub-features created in deep architecture can potentially be shared between multiple tasks. If we ask the basic question, what exactly is deep learning and why is it generally better? Short answers. This means using a neural network with several layers of nodes between input and output, and a series of layers between input and output do feature identification and processing in a series of stages, just as our brain seems to do. But multi-layer neural networks have been around for 25 years. What's exactly new? As we remember that they are very good with one layer, but these algorithms are not good at learning the weights for networks with more hidden layers. So again, what's new? The new thing is the algorithms. The algorithms for training for many layers have like improved the performance over the years. Deep learning actually learned the representations. So if we talk about a facial data set, we have different faces as the object models, but then it goes deeper in terms of object parts, which are actually a combination of different edges, and then goes deeper to edges and deeper to the pixel level. As we can see that in this image, we are taking this part of the image, which is going into and then all the parts are going in this one, and then smaller and smaller and smaller. We go deeper down to the pixel level. Convolutional layer filters work on every part of the image, so it just moves around here. Therefore, they are searching for the same features everywhere in the image. And to reduce the dimension, we use the max pooling, which usually present after the convolutional layer. It provides a downsampling of the convolution output. We randomly drop units along with their connections during training to add robustness, and we can also have fully connected layer, which each node is fully connected to all input nodes. Each node computes weighted sum of all input nodes. It has one-dimensional structure. It helps to classify input patterns with high-level features extracted by previous layers. So if we define the problem, lower-level operations in CNN, such as convolution, stride steps, pooling, backpropagation, etc., are implemented differently using different tricks in the available deep learning libraries. The output of any layer in CNN is related to the input size, larger of the row or the column, filter size F, larger the row or the column of the kernel filter, zero padding size P, and stride size S as given in this equation 1. Now, if the feature map size is floating point for any given scenario, it is desired to achieve integer value using certain operations. Among these operations, cropping and padding the input volume are the two well-known operations that are also implemented differently in order to handle input volumes when the stride layer, stride hyperparameter value gives a pre-calculated output that is not an integer. Now the question is, which one of the two operations, cropping or padding, will be more useful in the performance of CNN? Also, the question is to know what are the performance measures that can be improved with the proper choice of above operations. So the objective of the work is to investigate either cropping or padding is more effective in CNN performance. Also to investigate empirically the performance of two methods, cropping and padding, in CNN implementation for classification problem on a given data set. We'll also investigate performance measures are more affected by the change of the above mentioned hyperparameters. Talking about the experiment, we have used MATLAB library for CNN called matconv.net, found at this reference. The dataset is the well-known MNIST for handwritten digits containing 70,000 images of 28 by 28. The split was 60% for training, 25% for validation, and 50% for testing. The dataset was subjected to grayscale normalization to reduce the effect of illumination differences and also to make convergence faster using smaller range of data. We have used two models, implementation with cropping and with padding. In model 1, the output of the last pooling layer is cropped to meet the required integer size satisfying equation 1, while in model 2, the same goal is achieved by padding zeros in the input image. Also to note that we have not changed any other thing, including the weights. We have kept the weights same for both the model 1 and model 2, there was no regularization, and we just focused on the cropping and padding are the only two things that are changing. In table 1, parameters for each layer of the CNN used are displayed. For example, the first column represents the first convolutional layer with rectifier linear unit used at the neuron output. Size of the filter number 9 with depth 1 is the kernel size of the 2D filter used for convolution. 10 such filters are used in parallel. Stride of 1 is used for convolution operation, and finally there is no zero padding used at the output layer, output of first layer. In table 2, size of output for each layer during the forward pass is mentioned along with the gradient image size used for backpropagation of error during the backward pass. Starting from the left, the first figure shows the cost function change with respect to epoch in training and validation phases. Second figure shows the increase in accuracy with respect to epochs for the highest one among various Monte Carlo runs. Third figure shows the average accuracy of the top 5 best performance in the various Monte Carlo runs. This table shows the output size for the model 2, similar to what mentioned in table 2. And these figures show similar results just as in model 1. The left 3 bars are showing accuracy for training, validation, and testing of model 1, while the right 3 bars shows for model 2. If we compare the testing accuracy of the two models, this one, we can see that model 1 has an accuracy of 82% and model 2 has an accuracy of 86%. So we can conclude that the poor performance of like any CNN is not entirely due to the chosen set of hyperparameters that don't fit neatly and symmetrically on input volumes, but it also is partially due to the internal implementation of the CNN, especially for how the CNN internally handle this type of hyperparameters through all layers. This work has also proved empirically that the performance based on such type of hyperparameter will partially depend on how the CNN was implemented internally. This obtained result proved that the implementation of model 2 with padding is more efficient than model 1 with cropping in terms of classification accuracy, processing time, and generation. The main reason goes back to the fact that the model 1 backward pass, there were 25% of local errors were set to 0, meaning that 25% of its neurons are not updated, and this affected its predictive power. For model 2, on the other hand, none of the local errors was 0, hence all the parameters were updated, giving the model more predictive power.
Sorry, I think the last bit went a bit quiet. Okay. So thanks, Dr. Saad, for sharing very interesting thoughts on this cropping and padding. So I think that because the last part was cropped, I think which is the most interesting. Can you elaborate a little bit on why we are getting the padding result, which is model 2, slightly superior than choosing the cropping methods? Either Prof. Muhammad or Dr. Saad can please answer.
So, okay, thank you very much. I think Dr. Moeen can jump in here easily.
Yeah. Okay. Assalamu alaikum. Thank you very much to invite me on this conference. So just to give a last comment, which Dr. Saad was explaining, since in model 2 we are using padding, we are not dropping any of the element. So the gradient which we are calculating in updating the weights, they are participating in the weight update equation. So that's the reason in cropping what we are doing, we are dropping some of the elements and their gradients are not participating in the weight update. So this is the main reason which is the finding of this work, that the cropping is not suitable or not as efficient as padding. Although this work is dedicated for for one specific data, we need to explore more data or more different application in order to prove our claim. But with this data, we have proved that padding is more effective compared to cropping because of more gradient part is participating in the weight update.
I agree with your point. I think that
Like Dr. Tang has dropped his. Maybe the host can check. Okay. Can the host check if there's a question on the chat box? All right. So, like in short, it was about not choosing the cropping because it is like cutting off some data, and the padding was keeping all the data available, and we were like getting better results because we're not dropping anything. We're keeping the whole data available. Can the host check if there are any questions on the QA?
Sorry. Hello.
All right.
So sorry.
I was doing the duty for the chair.
I apologize. Really, suddenly my
It's okay.
internet's dropped at that point. So
It's okay.
Uh,
So, is there a question from the audience? Yeah.
yeah. So let me check. I think that probably no. I just wonder if the for the record, if the organizer can you set up like a Microsoft team where we can invite all the speakers here and take a photo. Is it possible? Dr. Saad, do you know if we can do that, or I can't hear you actually, Dr. Saad.
Are the other presenters available in the green room? Hosts?
I don't know if that's
No, we cannot know right now. So we can take a screenshot for this one at least.
okay. Yeah, just screenshots on 3 of us.
Okay, 3, 2, 1. All right, thank you.
Thank you, Dr. Saad. I think thanks for all the speakers for this noon. I think that we can take a short break, and please join the main sessions at 2 o'clock. I think that there will be the official launch of ESCON 2021. So thanks again.
Thank you.
Thank you very much.
Dr. Main, thank you very much. Thank you.
Thank you.
Thank you.